Hey, good morning, everyone, and welcome to our event this morning. We'll be talking about causal modeling in machine learning with Robert Ness. Uh, let's wait a couple of minutes to get everyone into the room. I see folks are still joining, and then we'll just jump right in. In the meantime, feel free to chime in on the chat and say hi. How's everyone doing this morning? Ravi's in Bangalore. What time is it there, Ravi? Scott's in Raleigh. Welcome, Scott. Nice. Bonjour, Marc-Antoine. Ça va? Ça va bien, merci. Wait another 30 seconds or so before we get going. We are, as you've noticed, if you've joined any of our online events previously, we are experimenting with a new platform as an alternative to Zoom. This is Crowdcast. There are aspects that we really like about it. In particular, the engagement model via the chat seems a lot more inviting than Zoom in a lot of ways. But I apologize in advance for any hiccups that we experienced this morning. I will just spend a few minutes introducing Twiml for those who aren't familiar with us. And then I will introduce Robert and we'll dig into our topic for today. So for those of you who are not familiar with Twiml and the podcast, we are here to help you and the rest of our community together grow in our knowledge of machine learning and AI. And in particular for us, it's really all about trying to make the world a better place, and in particular trying to make AI as it evolves a reflection of the world that we all want to live in. And we think the way to do that is by sharing the voices of a broad and diverse spectrum of ML and AI practitioners and researchers and innovators. And so if you haven't checked out the podcast, please do. Please subscribe, and please let me know what you think about it, what you like, what you don't like. I am accessible to you, sam@twimlai.com, or many, many other ways to reach me. Twiml is a lot more than just the podcast. We are an active community as well. First and foremost, that's about the people that come together to learn and grow and explore and share. Often that's via online courses and study groups like the one we'll be talking about today that Robert will be leading. But we've also got a very vibrant Slack group. That is the way to join that. If you are not already a part of that, is via twimlai.com/community. You will receive an invitation to the Slack when you join our free community. In addition to our educational programs, we also host events. Some of them are online events like this webinar or discussion groups, but we've also got larger conferences that we host, and we've got a really exciting one coming up this fall in October. This is a new event for us. It's called Twiml Fest, and really it's a celebration of our community, and that includes all of you. We'll be doing live interviews and discussions and meetups and a bunch of fun activities like AI trivia and happy hours, and we're working on an AI comedy event. So it's going to be a really cool 3 weeks of community-oriented, engaging, and fun activities. And you're invited not only to join us for the event, but also to help us create it. If you visit this site, twimlfest.com, you can submit a proposal for hosting a session that revolves around your own passions and experience, and we would love for you to do that. So at this point, I would like to introduce Robert, and let me see if I can get him on the screen here. Let's see. It's now asking Robert to join, hopefully. Hey, Robert. Can't hear you.
How about now?
Yes.
Okay.
Very clear, very clear. Welcome.
Thanks, Sam, for having me on.
Absolutely. So this is maybe the third of these webinars that we've done. This collaboration began in a little impromptu meetup that we had, Robert and I had back in NeurIPS in Vancouver, where he explained that he was building out this course and a topic that was really interesting, both obviously to him, but also to me and to our community. And I explained that we were looking to launch our educational programs and build on the study groups that we've been building. And now we're about to launch the third cohort of folks going through this causality course. And we'll be spending a lot of time talking about what is causality, if you're not familiar with it, as well as the course. But Robert, why don't you take a couple of minutes to just introduce yourself and let folks know who you are and what you're up to.
Yeah, great. So I'm a machine learning research engineer. I'm focused on causal modeling and probabilistic programming. I work at an AI startup here in Boston, focused on NLP, called Gamelon. Work mostly in Python on AI chatbot-ish kind of stuff. I also teach graduate courses at Northeastern University, PhD statistician. So I kind of come at AI from a more probabilistic machine learning kind of viewpoint. Kind of personal things about myself. My wife's a computer scientist. I speak Mandarin. I'm really into functional programming. I don't know. Is that informative? I always feel weird when I'm asked that. I'm like, I don't know what to say.
Yeah, absolutely. So that is very good. I had one more slide, but the slide is just to pull up a poll, which we'd like to learn a little bit about all of you now that you've learned a bit about us. I guess I didn't introduce myself. I'm Sam Charrington, founder of Twiml and host of the Twiml AI podcast. Can you see this poll? There should be a little button on the bottom of the screen that says polls, and at least one first person has found it, a graduate student. please take a moment to fill in the poll, and if other is your choice, feel free to chime in with more detail in the chat.
This is cool.
A pretty interesting spread. Okay, well, I'm curious about the other. If you would, I guess you don't have to, I'm not going to call you out, but if you're willing to let us know in the chat what we missed. But looks like
this is actually useful that I see, like, okay, so far we're skewing towards data scientists, machine learning engineers. This is helping me kind of tune my talk a little bit. This is actually pretty cool.
And we'll get into all of the reasons why Robert is a great instructor, although he probably won't spend a lot of time on that. But one of the things that we've heard as we've surveyed folks who have gone through the first couple of rounds of the Causality course is that he does just that, really tunes the presentations to the audience, to the folks that are in the course, and in particular, some of their, the problems that they're trying to solve at work, the problems that they're trying to solve, as their little side research projects. And so I expect we'll see some of that today as well. All right, cool. So it looks like about 40% data scientist, ML engineer, 15% researcher, 15% graduate student. Of course, these are all small numbers in terms of the actual numbers of votes. An IT program manager, consultant, and a mysterious unidentified other. Cool. So I think, Robert, I will turn things over to you. If you haven't found how to share your slides, it's just hover over your picture with the mouse. A little thing pops up at the top, and there is a share screen button with an arrow on it. You see that?
Yeah, it's a bit different from Zoom. 1 second here, let's try.
Yeah, take your time. And while we're getting Robert's slides up, if anyone in the audience would be willing to chime in on the chat about what they're looking to learn or what piqued their interest in this course, we would love to learn even more about you and your interests, and make sure we cover all that stuff as we dive into the webinar. Any takers on that?
Can you see my screen okay, by the way?
Yes.
Right.
And by all means, keep typing if you're typing. If not, as we dive into the webinar, if you have questions at any point, just chime in via that same chat, and we will try to make sure that you get your questions answered.
You know what? So why don't I just kind of get started here, and then Sam, just feel free to interrupt me when you want to bring it back to something more conversational.
Yeah, absolutely.
Yeah. So I got my screen here in play mode. Can you confirm that you see the full screen? Great. So I'll start by framing the problem a little bit from a machine learning AI perspective. The AI community is taking on causality. So we have a better articulation of the causal problems that we need to solve. So recently, Judea Pearl, kind of a forefather in causal inference, wrote a popular science book called The Book of Why. And towards the end, he talks briefly about artificial intelligence. He gives an example of how causality is needed to understand things like psychology, like things like intention, blame, regret. So he gives an example with a robot. He says, when my house robot turns on the vacuum cleaner while I'm still asleep and I tell it, you shouldn't have woken me up, I wanted to understand that the vacuuming was at fault, but I don't want it to interpret the complaint as an instruction never to vacuum the upstairs again. So that's you're, rather than just saying, track when the user says yes or no, rather it's saying, hey, understand the internal belief state of the user and introspect about what your own actions and why they would have had an adverse effect on the user. So don't just don't just stop vacuuming at this time or in this setting, but rather stop vacuuming when it's going to bother the user. Causality is also needed to understand physics, and by physics I mean often folk physics, right? Like simple mechanism, time and space, nothing complicated. But for example, Gary Marcus in a recent, again, popular science book called Rebooting AI, or rather a discussion about the book, he says we need to stop building computer systems that merely get better and better at detecting statistical patterns in data sets, often using an approach known as deep learning, and start building computer systems that from the moment of their assembly innately grasp three basic concepts: time, space, and causality. So that's Yasha Bengio. I'm sure people on this call would recognize him. Many of these people that we associate as being the leaders of deep learning are also diving into these causal tasks, right? So in a 2019 talk, Bengio says, once a machine can understand the causal structure of the world and produce plans to take advantage of the fact that they are not passive in the environment and can be active and acquire knowledge, we will be getting to a better standard of application. And in recent machine learning conferences, we see a lot of workshops, a lot of panels, some like this NeurOps workshop in 2018, which has several people who are well established in the causal inference community, but people like Bengio, people like David Bly. David Bly kind of is not new to causality, but we might think of him more as a kind of topics model, latent variable models kind of guy. Bernard Shokov, who's who started off making a name for himself in kernel methods, but now here he is and working on causality. We're seeing a lot of cross-pollination between what was historically two separate communities. And then finally, as we've probably more poignant this year than any other before that, we're starting to understand the problem of algorithmic bias and AI fairness. Causality has a lot to say about this. So on the bottom left here, you see this image from a ProPublica article in 2016 where a algorithm that was designed to predict somebody's risk of recidivism, that is to say that if they were released on parole, what is their probability of reoffending? You would see if you held everything else constant and just looked at except for race, right? You would see different disproportion. You would see people with the same profile. Oftentimes, you would see people of color with less obviously, less criminal history, getting higher risks of recidivism from this black box model. So what one does is say, okay, well, let's analyze the model itself and figure out, is this some kind of artifact of just random statistical or spurious correlation or bias in the data that is out of control of the user, or is there, for example, some kind of direct discrimination happening and representing that direct discrimination in the form of a causal graph, and then reasoning on that graph. So this is kind of my typical. This is a slide deck that I've used a few times, but this time I'm giving it. I know I'm gonna add a little. I want to put in a little bit of buffer so that we can have some more conversations. So I'm gonna really just focus on these first two parts. What is a causal model, and what can it do that deep learning can't do? And what are the big tech companies doing about causality? That gives us a little bit of context about what's happening in the real world in terms of jobs and employers and real world problems. So to start, let's talk about the causal model and what it can do that deep learning can't do. So there are three levels generally of causal query. We're going to call these association, intervention, and multiverse counterfactual. I prepend multiverse there because the word counterfactual is a bit overloaded these days. So I wanted to just be explicit about that. So
that multiverse in the physics sense with multiple universes.
Yeah, like think Rick and Morty, like alternate realities.
Mm-hmm.
So association is, given some feature x equals x, predict some target y, right? So that's classical machine learning, right? So in plain words, we might say, given somebody's on an exercise regime, what BMI are they likely to have? And so with this type of problem, deep learning is extremely powerful because if X, for example, is multivariate, or the relationship between X and Y is highly nonlinear, deep learning by given X. Now, but everything below association, this is what we would call a causal model. And so the next level is intervention. We're going to say, if we force X to take some value, let's predict Y. So if we force somebody to start an exercise regime, what would be the effect on BMI? So the way to think about this and why this is hard to do with the standard machine learning approach is that when you force something, when you change something, when you fix the feature set, what you've done is potentially fixed it to a value that's outside of training data. So you've changed the process. You're by definition extrapolating from your training data and it's possible, especially say if X is multivariate, that you're picking something that's way outside of whatever multi-dimensional nonlinear curve is matching X to Y, right? And so so just like you learned in a basic regression class, if you fit a line and you try and predict something that's way outside that line, you're likely to have a lot of problems. And we'll dive into that a little bit. But and so the way you get past this is that you need your machine learning model. It needs to have a specific intervention model, which is to say that it requires explicit modeling of cause and effect relationships. And then finally, we have the multiverse counterfactual. So this is saying, given X and Y, what would Y have been had X been different? Right. So like given my current, this is me, say, for example, I've been stuck at home because of coronavirus. Maybe I put on some weight. I'm thinking like, all right, well, here's the situation right now. I'm standing on a scale, and then I think to myself, what would my weights be had I, bought some kettlebells back in February and did some, high intensity workouts at home every day. Right. So I'm reasoning about my life in an alternate reality, but not only I'm not just simulating what happened in an alternate reality. I'm also bringing in evidence from this reality. I'm thinking like, well, here's what I know about what did happen under different circumstances. How would it have happened had I somehow had those kettlebells? So, right. So like there's information from this world. It needs to somehow penetrate that simulation of what would happen in the other world. And so this not only requires an explicit model of cause and effect relationships, but it needs a way of taking evidence from what we've observed to use that to flavor our imagining of what happened in the alternative world. And we want to do this in a kind of algorithmically sound way. So let's use a
quick question for you. Given your explanation around intervention and the idea that where it breaks the most is when your data is outside of your training data, is the idea there, I guess what I'm getting at is there's, even if you're within the bounds of your training data, you can still make predictions that aren't in line with any kind of causal relationship. And where does, how do you know if you're, or where is that, what do we call that, or how do we identify when that's happening? Does that make sense?
So let's think of so we have the training data. And one thing that, if you've approached machine learning from a generative machine learning or a model-based machine learning standpoint, somebody might have told you that don't just model the data, model the process that generated the data, right? So the process that generated the data, there's going to be some kind of joint probability distribution for all the variables in the training data. And so what happens when you do the intervention is you are now interfering in that process. And so you are by definition changing the joint probability distribution of all the variables in the data. And so you get a new distribution, and we call that an intervention distribution. And so now that we have two distributions, one way you can think about it is, okay, well, what is the KL divergence between these two different distributions? Or is there some kind of distance metric I can say between the process that generated the data and this new process that has me as an agent interacting with the data? And if that distance is close, then you're probably safe. And if the distance is far, then you're probably going to have problems.
Got it. And then we've got a question in from Ben. How would the counterfactual model work if we interleave time, or are these models only considering non-temporal data? What's the role of time here?
You can make time explicit or non-explicit. It's as a variable in the system. It's up to you. So, say for example, one of the more traditional approaches to causal modeling from a more generative modeling standpoint is causal graphical models or causal Bayesian networks, depending on what you want to call them. And those models can be applied in dynamic settings. And so, so another example might be something like, say for example, if a hidden Markov model, for example, which has specific time points. So if I look, just to show a picture here of don't get distracted with the content here. This is like a graphical representation. Actually, let's go back up here. This is better. So here we have graphical. So in causal modeling, you see a lot of graphs. And so here we have some kind of graphical representation of causality in the system. We might take a probabilistic graphical modeling approach to reasoning about causality here. Well, these variables can have little indexes corresponding to a time point. They could be discrete time, and then if you wanted to get fancy, it could be continuous time.
Great.
And so once you make the time representation explicit, then none of the reasoning algorithms change.
Okay.
Any other questions?
No, continue.
So I wanted to show a computer vision model, right? And so what we're going to do is imagine here that we have some kind of causal process that's generating a training data set of images of boxers. And you suppose here that we have this node here corresponds to a random variable for pixels. So this is just a tensor representation of an image. And we have, say, 3 causal factors here. We have, say, type, whether or not the image is somebody training or they're bloodied in some sense or they're posing. Then we have gender and ethnicity. We have this bidirected edge here. This kind of graph here is called an ancestral graph. It means that there's some causal factors here that affect both gender and ethnicity that are not being captured explicitly in the model. But we're going to think of this as kind of a representation of the joint distribution and that generates the data, as well as a causal representation of the causal relationships here. And so we can think of what happens in terms of association, intervention, and the counterfactual when we sample from this distribution. So if we just sample from it randomly, what we'll see is we'll see probably so images kind of heavily skewed towards black and white males. We'll see a variety of image types. If we were to go in here and say fix gender to be fixed at female, then what would happen here is that this statistical relationship between gender and ethnicity through some kind of unobserved common cause gets broken, and we fix gender, and we're seeing variation. We're seeing variation in the image that's where gender is fixed, but it's no longer that gender is fixing is not going to impact type, and it's not going to impact ethnicity in a sense because it's not going to statistically impact ethnicity in a sense because we've done that intervention. And then finally, we have this idea of the multiverse counterfactual. So this is where things can get a little bit weird, but we're saying like, all right, well, here's an image. So, imagine you had an app, right, where you uploaded an image and you could say like, all right, well, here's an image of a white female. Let's, what would this image have looked like if it were an Asian female? And it would sample from that distribution. This obviously these kind of ideas become a little bit hairy here, and kind of getting a model to work like this would, what does it mean to do an intervention on race, for example? Are we talking about, a genetic ancestral race, or are we talking about just features in the latent space that correspond to elements of the image? That's the challenge that we have when we kind of model problems like this. And of course, we know that generative deep learning can do this if you have the right curated data set and you have certain loss functions. But in order for that to work, what you have to do is, you have to do all that efforts kind of constructing that data set, but also you would have to have that question, say, that counterfactual question or about ethnicity, or that intervention question about gender, be defined a priori, and then have the training set target those queries. While a proper causal model can answer any ad hoc query, or rather any post hoc query after you train the model. And so that would be the advantage of this kinds of model. So any questions about that? Let's move on quickly. I heard somebody take it in. I heard an intake of breath.
That must have been me.
Okay. All right.
I don't know if anyone else's mic is live, but I think one of the things that about this course is that thinking about these types of representations of models and generative processes and the multiverse counterfactuals. This is all kind of new language that takes a while to wrap your head around. Is this stuff that you assume in the course, or do you spend a lot of time developing into it?
Oh no, we define these things explicitly, right? And we talk about them. So what's interesting about the course is, like last time, we had a kind of discussion session, and we talked about Richard Sutton's essay, The Bitter Lesson, where he says that anytime you're trying to solve a problem using human knowledge or domain knowledge, you're kind of wasting your time if that problem can eventually be solved by computing, because computing resources just get cheaper and more available. And so, there's one of the things, there's a little bit of controversy about this table, in the sense that there are some people that believe that you don't need to kind of, so these levels here imply different modeling assumptions, and they assume different levels of prior knowledge, human domain knowledge, and they're saying like, well, that's bad. We should just try to create better black box models that can kind of brute force this stuff through computing. And so we first off, we look at that kind of rigorously. We say like, okay, well, we have this idea. Is there an identifiability issue here? Is there something that you simply cannot learn given infinite data? And then number two, we'll start looking at like, well, are there ways to kind of relax levels of this ladder, kind of bringing in certain kinds of inductive biases from machine learning, so that we can identify areas of human knowledge and human domain knowledge that we can replace with more compute, stuff like that. I think so. Not only do we define these ideas, and then we kind of contextualize them within current conversations in machine learning. So we don't. This is not all assume that you know this stuff, and then we're just gonna kind of dive into applied problems.
Yep. Ben is asking, how do confounding variables figure into this, causal models? Does it still work with confounders?
Yes, and then so when I say an unobserved common cause, that's another word for that is a confounder, more specifically a latent confounder, and it affects your ability to answer the question given the data that you have. And we talk at length about that in the course. In this case, I assume that you already had like a ground truth generative model, but if you don't have, if you say, for example, all you had was a graph and you had some data and you wanted to answer a causal query, then things like confounding become your primary concern.
All right. And then Kia is asking, how is this approach to causality, how does this compare and contrast with Bayesian probabilistic models from Carnegie Mellon? I don't know, have you talked about an approach yet, or are you just kind of laying groundwork and doing basic terminology? And more broadly, is your course grounded in a particular approach, or are you serving, the various approaches that are out there?
Yeah, I guess the easiest way to express this show. So to answer the question, so when the woman, I think you said it was a she, right?
I said the name was Kia.
Kia. Well, I'm going to assume that's a woman's name, and sorry if it's not. That I think she's asking about. So when I think of CMU's, as to some extent, University of Pittsburgh's kind of approach to, it's called the Pittsburgh approach to causal modeling. It's a very graphical models based approach. Where you're not just, most everybody who works in this community is in the causal inference research community is comfortable with the idea of using a causal directed graph to represent your assumptions about causality. Where the controversy kind of comes up is solving causal inference problems by algorithmically reasoning on the graph, or fitting a model on the graph. This course assumes that that's the approach that we take in this course. And yes, I would say like that is the CMU/Pitt approach to the problem, as opposed to, say, for example, a Harvard School of Public Health approach to the problem, which is something called potential outcomes, or the Rubin-Newman causal modeling framework. And so, the reason that we take that approach in this course is because we're coming at it from the perspective of machine learning, of artificial intelligence. Graphical models are they're basically like the first expert system that we had in AI history that worked, right? That can kind of handle first order logical queries in a probabilistic way that made them robust, and that we could train on data. And the way that looks like now, what that looks like nowadays is, within machine learning, is model-based machine learning, generative modeling, variational autoencoders, all of these kinds of latent variable modeling approaches, or graphical modeling approaches, hidden Markov models, Gaussian mixture models, mixed membership models, all of these, probabilistic programming, all of these are direct descendants of that graphical approach to machine learning. And so we contextualize a problem within that generative machine learning / model-based machine learning context. But it's important to be able to speak the language of other people working on these problems. So blending causal reasoning and generative machine learning. But when we get down to, we do spend some time understanding what the other approaches are and explaining the core ideas there, and then how they translate to the concepts that we've already learned. It's, to me, as an instructor, it's important to make it so that people who are trained in this other approach to causal modeling, particularly, you'll see this a lot in industry, people who are trained in economics, for example, or econometricians, for example, that they're going to say words and have vocabulary that are different from the graphical approach. And it's important that we can understand those words and map them back to kind of graphical concepts. Does that make sense?
Great. Yep. Let's move on. We have a bunch more questions, but we'll work them in a bit.
Yeah. So I guess I'll get to the end of motivating the problem, then we'll just kind of open it up. So I do one more. So I want to give a real concrete example, Sam, that kind of gets at the question that you were answering. Like, so let's find an example where kind of traditional machine learning breaks down in practice and we need a causal approach. So here's an example where I'm going to train a machine learning model that predicts the weather. Every morning I'm going to wake up and take some barometer readings. Then I'm going to log whether or not it was sunny or it rained that day. Once I've collected enough data in my training block, I'm going to train it out. I'm going to train a predictor, and then I'm going to be able to predict, given the data that I get from my measurement device in the morning, to predict the weather that day. But the thing about machine learning is that we're always using it to do something, right? We're building software that either helps people make decisions or automates decisions. So what is the decision that we're going to make? We're going to decide whether or not to bring an umbrella with us that day. So in this first case, I took a measurement. The algorithm told me not to bring an umbrella. It was sunny, so I have a win. In the second case, the algorithm told me to bring an umbrella. It was rainy. I have a win. In the third case, it predicted to not bring an umbrella. It was rainy. I have a loss, et cetera, et cetera. Then once I've collected, so I'm now using the algorithm. It's live in production, but I'm still collecting data. More days happening. More measurement. Weather readings are being logged. And so now in this next training step, I'll just combine training block 1 and training block 2 again, and then train a new model with more data. And so this is standard practice. We'll just keep, as more data comes in, we'll keep updating our model. Now we look at a similar example where we look at where at the beginning of a quarter, I look at some business industry data about my industry and macroeconomic numbers, and then predict. And at the end of the quarter, I look at whether or not my sales went up or down. And sales going up is the same as sunny, and sales going down is the same as rainy. So we're basically getting the same kind of data in terms of positive and negatives, but we're just kind of different domains. Now the problem is that I'm going to use this data to predict whether or not to run an ad, because if my sales are going to go up, maybe I want to save money and not run ads. But if I think my sales are going to go down, then I should run some ads and try to convert more sales. The problem is that in this first case, the data doesn't care about the weather doesn't care about whether or not I bring an umbrella. In other words, my decision does not impact the weather. But in this case, my decision to run an ad will affect sales in the next quarter. So here I am coming in here, and my decision is now affecting the environment that generates the data. And you can think of this as kind of what happens when you put a microphone against the speaker, right? You get this kind of negative feedback loop, which can add significant bias towards your data. You see this a lot in credit fraud detection, right? Where if you're not careful, your algorithm just gets better and better at determining extreme cases of fraud, because you're already using your algorithm to filter a whole bunch of cases of fraud. So it starts to get biased towards really oddball cases of fraud, and then what happens is that some normal cases of fraud start to slip through. And so so you need all the techniques that people have to adjust for that. Something, for example, called propensity score matching, are basically causal inference techniques. And this has a lot of impact on reinforcement learning. So one of the things that we dive deeply into the course, probably differentiates a lot from other workshops and courses, is our focus on machine learning problems, one of which is reinforcement learning. And one of the hypotheses I have is that one of the reasons we're having trouble seeing some reinforcement learning to get some traction in practice, or when we train things in simulation, it's really hard to get the transfer to the real world, is because we don't really have good causal models of an agent acting on its environment. So we talked about intervention. When an agent does an action, that's an intervention. And so similar in this case, if that action is affecting the environment, then your Bellman equation, the thing that you're trying to optimize in most reinforcement learning algorithms, is actually different from the Bellman equation that the agent is actually the ground truth Bellman equation. In other words, you're changing the Bellman equation every time you do an action. And so one of the things we address in the course is to say, all right, well, how can we model reinforcement learning if we make the actions explicit as interventions? And this do notation here means it's an intervention, and that's being driven by some policy that depends on state. If you're not familiar with the Bellman equation, don't worry about it. But it's just an extension of that sales example, except where you have an agent that's kind of learning a good policy. And so we went, and the gist here is that we went to reason counterfactually about our agents that we had in production. So we look at some log data and we say, all right, had we given this agent different decision-making policy, would it have done better? And we want the agent itself to reason counterfactually, which is to say, hey, I'm playing this game like Dota 2 or whatever, and I'm looking at my history of decisions and the results, and I say, hey, back then I did this thing because I thought it was the best thing to do given what I knew at the time, but given what I know now, I believe that I would have gotten a more reward had I done action A instead of action B. So I'm going to update my policy so I won't make that mistake again. And this is very much aligned with human reasoning, right? We kind of reason about our mistakes, given what we know, and say like, okay, I'm going to here's what would have happened in the alternative universe had I behaved differently. So I'm going to change my policy for dealing with these situations so that I get better outcomes. So as a last point, before we switch the conversation, I want to jump into kind of, what's happening at tech companies about causal inference. And the thing I'll say there is that kind of traditionally, because causal inference is a field developed in social science, econometrics, public health, it was kind of the challenge was to take statistical methods and build a semantics for making true causal inferences about the real world. People who tended to have this training tend to come from more experimental, more social science, more econometric backgrounds. And so within these companies, they tend to be on marketing science teams, experimentation teams. So this is a internship for Facebook, where it's looking for people with causal inference background. This is one for senior data science and Netflix, looking at product insights. So this is kind of where in some companies causal inference is being applied, not so much to build machine learning algorithms, but to conduct experiments on the hyperparameters that tune those algorithms. But generally speaking, there is this gap between you have your kind of data sciencey experimentation platform teams at companies who are trying to do what's essentially very fancy A/B testing in complex settings, and trying to bring causal inference ideas to bear on those questions, and that's separate from the machine learning engineering teams who are trying to build software, build algorithms that, say, for example, do recommendation. But because my prediction is that these two skill sets, or an intersection between these two skill sets, is going to be increasingly important going forward, and that is what we're trying to get at in this course. So not just doing theoretical and more researchy ideas, but really kind of getting into how can we use machine learning and causal modeling to solve practical problems. So with that, I'll open it up. Some more say here.
All right, great. Let's maybe take a couple of quick questions before we get into the details of the course itself. One question from Robbie is asking about how accurate are causal ML models, and I think the broader question there is: are we measuring accuracy, the same way, or is accuracy even the? Well, I think the causality is suggesting that accuracy is not the only question to answer when we're trying to apply these types of models. Is that fair?
I don't want to say, so I would say that like whenever from a practical standpoint, whenever you're optimizing for other things, like for example, constraining a model to map to certain causal assumptions, you're going to pay a price in predictive accuracy relative to an unconstrained model. But some might argue that price that you're paying, you're not actually paying a price, because what you're doing is, if those causal assumptions are true, then well, they should be first in the model. If they reduce accuracy, that accuracy is from overfitting anyway. One of the gains that you get from incorporating causal assumptions to a machine learning model is transfer learning, right? Transferability, right? So, if there's a causal relationship between, say, two entities in real life, that causal relationship is invariant. The effect of smoking on cancer, for example, is the same in China as it is in, Brazil. While of course, there's other confounding factors there, but like that direct relationship between smoking and cancer, we're going to expect to be invariant. And so that kind of causal invariance in the machine learning setting transfers to transferability in models. I expect my model, if my model is a good reflection of true causal relationships in the world, I should be able to train it on one data set and apply it to data collected in completely different settings, and it should still work well. Well, that is definitely not what we expect from your standard machine learning model.
Yeah. So we've got some questions about the course itself and prerequisites and the like. You already went through an outline of you kind of pulled up the course page itself. Do you want to, how'd you like to introduce the course in terms of the goals and the structure?
Let me answer that question in terms of prerequisites first. Okay. The prerequisites are really, you need to have a good understanding of probability distributions and random variables. And when I say good, I mean a foundational understanding. Like, you don't have to be a mathematical probabilist, but like you just need to know what a joint distribution is, a conditional probability distribution, what expectation is, what's the expected value of a distribution. There's not much in terms of calculus. Like, we tend to focus on discrete examples, so it's more like kind of discrete probability, like dice and cards kind of stuff. Because of course that all generalizes to continuous multivariate cases. The math is the same. It's just the computational complexity is higher. And so like just kind of a basic understanding of probability theory, conditional probability, joint probability, random variables, and Bayes' rule. Bayesian reasoning, Bayesian inference and Bayesian reasoning in general become important to understand at the fundamental level, in terms of just like knowing what Bayes' rule is and how, when you see, knowing the equation. We work a little bit with some probabilistic programming and inference on graphical models, and I try as hard as I can to make it so that you're not required to understand those inference algorithms. You can of course always look them up, but say for example, if we're using importance sampling or stochastic variational inference to solve a problem, I try to abstract the inference part away as much as I can, because it's not a class on Bayesian inference or probabilistic inference. It's a class on causal modeling. So of course, understanding that stuff will help you out, but it's not a prerequisite. So kind of introducing the course materials. So Let me run through that again, just because I breezed through it last time. But we start with, start talking about graphical models and what those graphical models say about conditional independence in the data that we're training our model on. Then we dive into the core assumptions of causal modeling. So these go beyond statistical assumptions. We tie this back into generative machine learning. We define clearly what an intervention is. We extend we extend from graphical models to probabilistic programming. So if we want to kind of relax the graphical assumption and work with programs, what does that look like? Talk about a specific modeling paradigm called structural causal models. And then we get into some of those bread and butter causal inference techniques. So if these are people, so the question about confounding, how does that affect here? This is all about confounding here. And it's interesting here because we find out that kind of common knowledge about how to adjust for confounding is wrong. And we show how, and we kind of show that rigorously and show how to get around that. And then towards the end, so this is kind of potential outcomes, statistical methods. Then towards the end, we get towards some of that more, sort of the multiverse counterfactual stuff and how we turn those into algorithms. And then we talk about decision theory, MDPs, and agent modeling, like in reinforcement learning. Every week we have a retro where we hop on a live call and talk about what was covered in the previous week. So this session will start from September 17th to December 10th, and every Thursday at 11 a.m. Eastern Time, 8 a.m. Pacific Time. Within that block, we'll have a retrospective where we're live, and I kind of do a quick overview of what we covered that week in case you missed it, and then we discuss it in a kind of conversational setting. That said, once this cohort closes, you get indefinite access to these materials. So a lot of folks are busy and they have to kind of take a break and come back, and so that's definitely open to you.
Not just the materials, but also the recordings of these retros. Is that right?
That's true. Yeah. So we so all of the retros are posted. So if you miss one, you can watch the recording.
And then since the one thing I thought was really interesting was the initial cohort of this course essentially kind of continued on as a community that reads causality papers together. And that's something that this course clearly has prepared folks to be able to do. Is that still ongoing?
That's still ongoing, yeah. That and anybody who wants to join that, they can join that. That's on Saturdays at 11 Eastern Time in the Twiml. You can just find that channel in the Twiml Slack. And yeah, we read papers. We also just kind of discuss high level ideas. Like there's a lot of people there who are interested in reinforcement learning. A few people who are interested in the relationship between cognitive science and computational cognitive science and causal reasoning, and so we have some pretty interesting conversations about those topics.
Great. Can you quickly pull up the course details in terms of the costs and where folks go to sign up? And we'll circle back to questions for folks that can stick around.
Yeah, I don't actually have the cost here. The full price is $1,200 for the 4-month cohort, and there's a 15% off for the Twiml community here on this call. There are 2 coupon codes, one for paying full price up front and one for monthly payments. So that's unlimited access, the weekly retros. You can schedule one-on-ones with me through the duration of the course. This is useful for people who have, say, work-related problems that they want some consultation on. You can engage with me and other students through the course forum. There's some assignments and a capstone project, those get evaluated by humans. Of course, then you have access to that forum as well.
Cool.
Also, people who, I'll point out that a lot of the materials that we use in the course, some of the past projects from other students, they're here there's some tutorials and some tools. Those are free and they're in this repo here if you wanted to check them out.
Cool. Why don't you put that the pointer to the sign up page? I guess the page is twimlai.com/causal. And we will continue here answering folks' questions. Robert, in this version of the webinar, you skipped what we've covered in the past in terms of the computational side of this. And CJ has a question about the top Python libraries for causal modeling and ML. If I remember correctly, the ones that you have recommended in the past include Pyro and PyMC, is it? And can't think of a third.
So in the course, I use two languages, one called, so one is Pyro, which is a PyTorch-based probabilistic programming language. I don't use PyMC. Pyro is the only probabilistic there's another one in Julia, but Pyro is the only, tensor-based probabilistic programming language that I know of that has the abstractions that we need to model, the three steps of that tier in the causal query, like the interventions, specifically to have an intervention abstraction. None of the other probabilistic programming languages that are kind of using for example, TensorFlow doesn't have that. To my knowledge, we use those probabilistic programming languages because they help us build the algorithms. Now that said, there's a lot of tools out there that would let you that actually are wrappers around, kind of already encode the core kind of algorithms themselves, and are just kind of you have a kind of specific causal query that you want, and you specify the inputs, and it gives you the outputs. So something like DoY, which is from Microsoft Research, main developer there is a really clever guy named Amit Sharma. So that's an algorithm where that's a package where you can just import it and say, like, here's the causal question I have given this data, can I answer it, and what is the answer? And it'll just do that for you. We don't that kind of very high level interface we don't work with so much in the course because we actually want to learn how these things work. But there are, but if you're interested in causal inference in a practical setting, there's plenty of tools out there that you can work with.
Cool. Jeremy is asking, does this course tie together with Rubin's causal modeling, or does this course tie together the Rubin causal modeling with Pearl's graphical do calculus approach?
Section here. So Rubin's causal modeling is also called a potential outcomes framework. And we kind of talk about like this generative machine learning thinking versus the population-based thinking that statisticians tend to have. Like in that Rubin causal modeling framework, it's basically you want what your goal there is to kind of view causal inference as a missing data problem, and establish what assumptions that you need to make to attack it like a missing data problem, and so that brings to bear the kind of general tools of it contextualizes it within a very old statistical context. We're taking a generative machine learning approach to it, but we'll talk about how the two connect to one another, and there are theoretical connections that are worth understanding.
Got it. Can you talk a little bit about how causal modeling can help address explainability or interpretability of non-transparent ML algorithms like deep learning?
Yes, because so generally the way to think about it is So before I showed you, let me give a very high level answer. So before I showed you kind of causal graphs and where nodes in the graph corresponded to components of some data generating process, one node that we can create is the prediction of a black box algorithm given excuse me, some other nodes and the inputs from other nodes in the system, which would be features for that algorithm. And then we can have the other node for the actual outcome. And, and then we can kind of draw causal edges between all these things representing our assumptions. And then, say, for example, reason about the actual outcome and the predicted outcome, and using queries on this model that say like, this, we assume that these two things, so what counterfactually speaking, like, all right, the person had this profile. What would this profile would look like if the gender was female, for example, instead of male, right? And then we can kind of look at the predicted outcome and the actual outcome, and then reason about what the algorithm is doing if it's biased, for example. Great. Or if it's actively discriminating, for example.
All right, great. Any final questions about the course itself? I don't think you covered it this time, but you do offer a refund policy for folks that are unsure. Can you maybe take a second to mention that?
Yes, 30-day refund policy. There's no question asked there. Just within 30 days. And the other issue is, and I forgot to mention, there's a student discount. So the full price student discount is $750. $750, and you just, to get that, you just need to verify with a student ID, and that's all you need.
Oh, nice. Jeremy's asking, how much time per week should students expect to spend on the class?
The course was originally designed as a advanced topics graduate school course. So it would it's designed to occupy as much. So from my perspective as an instructor, it's designed to occupy as much time as it takes to deliver that lecture in a offline setting. Whatever, I'm almost forgotten what that feels like nowadays. And now, of course, a graduate student would actually would be required to do assignments and do a capstone project, and so that's probably where they'd be spending most of their time. While a person who wanted to take a more casual overview, or who had other time commitments and didn't want to go that deeply into the assignments, could instead say just read through the lecture notes and watch the videos, and maybe kind of sign in for that hour-and-a-half long retro each week, and that would be so that would be at the more minimal end of involvement. You'd still get a lot out of that if that's what you wanted to do. Especially if you scheduled a few calls that were kind of related to problems that you're actually working on, because then you can contextualize it within your own life.
And we've seen folks take both approaches, just kind of casually sit in on the course and consume materials and leave with a understanding of the foundational elements of this, that they can give them the vocabulary and allow them to engage in conversations. And we've seen folks on the other end of the spectrum really dive in and, end up writing papers or working on, applying it to side projects or applying it to work projects. I think it's run the spectrum.
Yeah, I've actually written 2 papers with former students. And
So awesome.
that's not a promise that if you take this course, you will publish in Neurops. I don't, I do that. I did those because I really like those students and they had cool problems. And
Nice.
I'm kind of I'm an engineer who works in industry, but I work in a startup where we don't write, if you're in a startup with a limited amount of runway and you're trying to deliver product, nobody's encouraging you to write papers. But so it was more of a kind of spare time thing because they were cool problems.
Awesome. We'll take a couple last very quick questions from Shamal. Does Judea Pearl know about your course? Have you showed it to him?
I've interacted with him on Twitter on substantial conversations about causality, but I don't know if he knows about my course.
And have you looked at the Microsoft package to do why repo on GitHub?
Yeah, that's the one I just mentioned, DoWhy by SR, led by Amit Sharma. That's a cool package.
Awesome. All right.
There's also one if the people from a more kind of businessy background might be interested in a package called Causal NEX by Quantum Black, which is the more quantitative arm of McKinsey & Co. Mm-hmm. And I think so they're more focused on structure learning, like learning causal structure from observational data, and then using that to drive business analysis. I think it's interesting. I talked to these guys a few times at conferences. My PhD research was in causal discovery, structural learning, but I was focused mostly on natural science problems. So, seeing it being applied in that setting is actually pretty interesting. So that might be another thing to look into.
Cool. Well, everyone, thanks so much for sticking with us this morning, afternoon, evening, depending on where you are. That last one, Jeremy, was Causal NEX by Quantum Black, NEX. Robert and I are available on the Twiml Slack if you have any further questions. Robert, thanks so much once again. Always great chatting causality with you and introducing a new cohort of folks to this course.
Thank you, Sam. This was awesome.
Awesome. All right. Thanks, everyone. We'll send out the recording as well if you care to take a look at this again.